Welcome everyone. So today in lecture number 27 we are going to summarize of whatever we have learned and deduced so far. So today this would be a short lecture where we only discuss about the gist of the wave functions of the rigid rotor. Okay, so we started with this Schrodinger equation H psi is equal to E psi, and we understood that the psi is a function of theta and phi, and then we expressed the Hamiltonian operator like this. So this is basically the Laplacian operator in polar form with constant r. Okay, so this is getting operated on psi theta phi. Now by convention the psi theta phi is expressed as uppercase Y ln theta phi. So this is just a convention. So actually these are psi wave functions, psi theta phi, but the majority of the textbooks follow this symbol Y ln just for the wave functions for rigid rotor is equal to E. Now we have already found out that the energy, if we solve this, it will come down to h cross square by 2y L into L plus 1 multiplied by this wave function y ln theta phi. And now the generalized expression of y ln theta phi. So this is the normalization constant. Okay, so this is the general expression, and you see the normalization constant that I have wrote in lecture number 26. This is slightly different because now here at the denominator we have the 4 pi term here, because you remember that there was a normalization term of 1 over root over 2 pi for e to the power I of phi, so it has been included here, just that has been included here in the denominator. So in total the normalization constant looks like this. So the normalization constant is a function of ln m, we can clearly see, and now we have this part PLM cos theta. So this is nothing but the Legendre polynomial expression. All right. So this is a function of cos theta. So depending on the values of L and M, we have an expression. We have a function for cos theta. So it could be just a number 1, could be 0, could be cos theta, could be sin theta cos theta, something like that. Okay. And the phi part is always e to the power I of phi. You know what the most striking part of it? Probably you have noticed, if that is the generalized or the summary of the rigid, the wave function for rigid rotor, means these are the solutions, or we can say these are the general solutions. Okay. And I also told you that when we study the hydrogen atom, the theta phi part means psi theta phi would be exactly like this. Okay, because we would assume that keeping the nucleus fixed, the electron of the hydrogen atom is rotating. So here what's happening, that for a diatomic rigid rotor, you can think about this is a diatomic rigid rotor, so it is rotating like this. All right, but when we talk about the hydrogen atom, what would happen, that this is the nucleus and this is the electron, so we may think that now electron can rotate around the nucleus by keeping the nucleus fixed. So the theta phi part for a diatomic rigid rotor would be exactly identical with that of hydrogen atom. So for hydrogen atom, whatever the wave function is, the y ln theta phi part would be exactly the same what we are learning it here. Okay, so for hydrogen atom, we only need to find out the wave function depending on the radius, because that r vector is variable for hydrogen atom. So anyway, coming back, you know what is the most striking feature? Can you guess from this generalized solution? I'm sure you have noticed this by now. Because of the presence of this part I e to the power I m phi, all the general solutions, okay, are imaginary. All right. So doesn't that surprise you? Because very soon we'll be finding out that these will constitute the solutions of the wave functions for hydrogen atom. And from our +2 level of knowledge, we knew that the solutions of the hydrogen atoms means the solution of Schrodinger wave equation for hydrogen atom are nothing but they represent s orbital, p orbital, d orbital. Okay, and definitely those orbitals would have this y element theta phi, the angular part. But now here we find that these quantities or these solutions having YLM part, especially the phi part, imaginary. Okay, so then how can an imaginary solution can be applied to some real wave function that we actually experimentally observe, like s orbital, p orbital, d orbital? Okay, so here as of now it appears a great anomaly. Okay, but don't you worry about a thing. When we when we would study the hydrogen atom, we will definitely address this issue. Okay, so what happens to these imaginary solutions? All right, so anyway, we will catch that up later, but let's come back to one or two more generalized expressions, that is the condition for orthonormality. Or condition for orthogonality. Anyway, so the condition is obviously you have to integrate over the whole limit. The limit is 0 to pi for theta and 0 to 2 pi for phi. And then we have two arbitrary functions, y-lm, theta phi. All right. And then it is, multiplied with, instead of another thing like we can have n here and we can have k here, theta phi. And then we have the element, that is this dx part or d tau part of volume element. So here in this case we have sine theta d theta d phi. All right. So this is the integration element, and that should be equal to the Kronecker delta. So it should be delta Ln, and also it should be delta Mk as per our definition of Ln and Mk. All right. So in other words, we have to define that whenever this is 0. All right. So we have already knew that when L naught is equal to n and m naught is equal to k, those are non-zero, those will be 0. Yes. And whenever L is equal to n and m is equal to k, those should be 1. So that means those should be using, provided YLN and YMK are normalized. All right. So so far this has been a summary, but still there is one little aspect is left. What is that? The little aspect is I want to talk a little bit more about this thing, YLM theta phi, so this wave function. All right. So let's clean the board and just talk about it. Okay. So now, if you remember that in spherical coordinates, the volume element, okay, d tau, stands for r square sine theta dr d theta d phi. All right. So this is called the volume element. Good. And we have learned about it. Now if you think in case of rigid rotor, R is fixed. Okay. So R is constant. Now let's assume that R is equal to 1, means unity. Now if R becomes unity, then whatever the element of integration, that is sine theta d phi, we get, so we can call that it is dA. That means this is an area element, because if we multiply this thing with unity, which is R, that means another dimension, we get the volume. So if we divide a cubical dimension by a cubical dimension of length, if we divide it by a dimension of length, it becomes the length dimension of length square, which is area. So basically that's what it is all about. So now we understand that this is called an area element. Now what if I take the whole integration between the limits, that means the limit of theta is 0 to pi and for phi is 0 to 2 pi, and if we take the complete integration, okay, over the area element, this would come to 4 pi. Okay. Now if you look closely, what is this 4 pi value? This 4 pi could be very well that it is the total surface area of a sphere with radius r equals to unity. Isn't it? 4 pi r square. If r is equal to unity, then 4 pi becomes the total area of a sphere. So therefore, this value, that is sine theta d phi is equal to dA. It is also known as the area element of a sphere. Okay. So it can be further proved that this ylm theta phi, the wave functions, these are orthonormal over the spherical surface. Okay, so that spherical surface is defined by this spherical area element dA. All right. So in other words, that this ylm theta phi, this function, has something to do with an area of a sphere, okay, or better over a spherical surface. All right. So because of this reason, mathematically, this ylm theta phi is called spherical harmonics. Okay, this is a name came from the mathematics, because these are obtained or shown by the famous mathematician Laplace in 18th century, and so by his name we got this Laplacian operator. And this ylm theta phi is also called Laplace spherical harmonics. Okay, so in short, we call them spherical harmonics. Ylm theta phi. Okay, so now why does that spherical term come? Probably by following this argument, we have a little idea about it. Okay, so that's what I intended to provide you, a brief idea that a spherical surface is linked with the wave functions of ylm theta phi. Alright, and it is in fact coded in its element of integration. Alright, so now the last part. So let's summarize the list of some spherical harmonics for different values of L and M. So let's clean the board and do it. Okay, so before we proceed to the summary of the spherical harmonics, just let me remind you once again that the spherical harmonics are eigenfunction of L square operator. That means the square of the angular momentum operator. So here we can derive it easily that the Hamiltonian operator operating on y ln theta phi gives you the energy value, which is h cross square divided by 2y, L multiplied by L plus 1 times y ln theta phi. Okay, so we have already seen it. Now, remember, the Hamiltonian operator is nothing but minus h cross square 2y Laplacian operator. Okay, so this is the expression for kinetic energy in general. Now, for rigid rotor, we have already set the potential energy is equal to 0. So whatever the Hamiltonian is the Hamiltonian for rotational kinetic energy. So the rotational kinetic energy we have already used is L square by 2y. So here H is equal to basically L square by 2y, because the Hamiltonian for rigid rotor is basically the operator for rotational kinetic energy. So we can replace L square divided by 2y, YLM theta phi here is equal to h cross square divided by 2y L plus 1 YLM theta phi. Alright, you are with me now? We can easily write this equation into this equation by replacing h by L square over 2i. Now you see, this is an eigenvalue equation once again, and both sides we have the constant 2i. So they cancel out, and what we are left with, L square YLM theta phi is equal to h cross square L plus 1 YLM theta phi. Okay, so this is an easy equation, eigenvalue equation. Operator operating on wave function giving you this is the eigenvalue. Alright, so now whenever we have eigenvalue, that means corresponds to some observable. Okay, so observable means there should be an operator. Our operator means operator for a physical quantity, okay, that which we are going to measure. So therefore the operator L square actually is the operator for angular momentum square, L square. Okay, so definitely we get that if we want to measure the L square, now we are having the eigenvalue. Alright, so the value of L square we can directly equate is h cross square L multiplied by L plus 1. So this is the square of the angular momentum is equal to this. Okay, now this is a scalar quantity, remember. And then if I want to find the value of the angular momentum, simply it becomes h cross root over of L into L plus 1. Alright, and I'm sure you have already seen this expression, some of you, in hydrogen atom. Whenever we are asked to find the angular momentum of the electron when it is in p orbital, alright, or when it is in s orbital. So you find a value for L and you can calculate the magnitude, okay, magnitude of L. So whenever L is 0, you see L is equal to 0, and whenever L is 1, means this smaller case 1 is 1, you have L is equal to root 2 h cross. Okay, so we get a very important derivation here, and this equation is very useful in spectroscopy, molecular spectroscopy as well as atomic spectroscopy, that we find the value of angular momentum for diatomic rigid rotor, okay, from by solving the Schrodinger equation. Alright, so now is the time to get a list of the spherical harmonics for different L and M value. Okay, so here we are with the list of first few spherical harmonics. So if you put the value for n is equal to 0 and n is equal to 0 in the expression that I have already given, you should be able to find out this. Okay, now it's your turn to find out whether you get these expressions right from using those standard formulas. Okay, so this is the exercise you need to do. So y10 is this. See, it's cos theta here, sine theta e to the power I phi, sine theta e to the power minus I phi. So now you see here, looking at this general expression, whenever m value is a non-zero, so in these two places, m not is equal to 0. For an m non-zero value, my spherical harmonics, we can write spherical harmonics are imaginary. Okay, so this is a very important feature, and we need to find this out. That so if y11 or y1 minus 1 they represent px or py orbitals respectively. If they, we are going to find out. But if they represent those two orbitals, so what would happen? Because those are coming out as imaginary wave functions. Alright, so then how we deal with those in the hydrogen atoms. Okay, so probably if you look at any standard textbook where they list the wave functions for hydrogen atoms, they never list any imaginary functions. So those are all real functions. So we have still a good amount of study left. Okay, so that we are going to cover in our next few chapters, and very quickly we will be in the chapter of the hydrogen atom. So this is a chapter with long expressions, so you please follow those expressions closely with pen and paper. Try to deduce those small formulas from the bigger ones whenever applicable. All right, and please study hard and practicing hard, and we'll see you in lecture number 28 with some new and interesting topic. So till then, goodbye.